Hello, I'm Andrew Wentzel from the Electronic Visualization Lab at the University of Illinois, Chicago, and I will be presenting my group's work on designing for explainable data mining of spatial cohort data. This work was done in collaboration with the University of Iowa and the MD Anderson Cancer Center. In head and neck cancer, clinicians often rely on radiation therapy to target tumors in areas that can't be removed through surgery. These treatment approaches seek to deliver radiation to the main tumor while minimizing radiation delivered to other organs. Despite this, radiation can still cause collateral damage that leads to serious long-term side effects, such as dry mouth, trouble swallowing, trouble speaking, mucus, and pain. Therefore, understanding the conditions that lead to permanent side effects is important for creating better treatment plans. Imagine Dr. Anderson is deciding on a treatment plan for their patient. While all treatment plans may have equal chance of tumor control, each treatment may result in higher risks of side effects such as dry mouth or swallowing problems. If Dr. Anderson knew the patient's risk of developing specific side effects, they would be able to give the patient additional preventative therapy to help ease or prevent side effects before they become permanent or serious. One method that clinicians use is by assigning the patient to different risk groups using examples from previous patients. Identifying high-risk patients is a common task in clinical care, usually performed by clustering patients into subgroups that represent subsets of each population. This allows clinicians to better assess patient risk and prescribe treatment by looking at similar patients. Although clustering algorithms are well researched, in this case, it's also essential to carefully consider the features and the similarity measure used when clustering the patients. Specifically, for radiation therapy data, clusters need to carefully consider the spatial dose distribution to key organs. For example, models predicting severe dry mouth should consider the doses and severity of damage to nearby organs responsible for saliva production. Overall, when developing cluster models for clinical applications, care needs to be taken when selecting the features used for clustering. Although automated feature selection methods exist, since we are using unsupervised clustering, it's important that our clusters only consider the most relevant dose features for selecting the high-risk patients. This generally requires understanding what organs are related to each symptom and which levels of dose received can cause dose damage. Including domain knowledge into the feature selection process is important, as, due to the sparse and high-dimensional nature of the data, statistical feature selection methods often overfit the data, making future models generalize poorly due to data drift or changes to existing treatment practices. As a result, it's important that the features used in each cluster are directly related to organ damage in the cluster and outcome of interest. Additionally, since we are using treatment data, much of the existing knowledge of when doses may cause side effects is embedded in the treatment plans. As a result, doses to these organs are confounded by other factors such as overall tumor severity. Finally, some clustering models may perform well in terms of performance metrics for predicting an outcome. However, the cost of treating an at-risk patient is usually different than the cost of not treating an at-risk patient, and useful clusters need to clearly identify high-risk groups that receive treatment and low-risk groups that don't, which is difficult to capture using standard objective functions. For example, models with more clusters may perform better in terms of AUC or correlation with an outcome, but the additional clusters may not be useful for clinicians when deciding on treatment plans when they don't have a clear high-risk or low-risk group. In this case, it may be better to use a lower-performing set of clusters with a more useful distribution of patients that have a clearly defined high-risk group that receives treatment. Typically, a workflow for designing these clusters uses a time-consuming approach for building clinical usable models, in which model builders and oncologists have to repeatedly work together to identify large sets of plausible features and model parameters, and select the best model through some kind of automated grid search using a single heuristic. Then, after analyzing the resulting model, changes are identified and used to iterate on the original model parameters. This workflow is generally time-consuming because the goals of the models for clinicians often don't align with the quantitative goals used by model builders. Often, visualization only applies in the process of analyzing and communicating the final results so that they can be interpreted. However, in our work, we want to integrate the entire model building loop into a visual computing system that integrates inputs from all groups at each step of the process. In this work, we present a visual steering approach for creating patient stratifications of head and neck cancer patients, separate patients at high risk of experiencing long-term side effects. Unlike the current state of the art, our approach supports interactively exploring spatial dose distributions, along with temporal symptom outcomes. Our system also uses unsupervised rule generation to help explain our clusters and iteratively refine model parameters to create actionable stratifications. In our evaluation, we describe 2 case studies of applying DASS and show how it has been used to improve existing outcome models. Finally, we provide design lessons gained through this collaborative design. Related work in this field includes prior approaches for visual cohort clustering with temporal health record data and shape features. For medical images, visual systems have been built for tissue imaging and bladder cancer. However, most of these works don't deal with high-dimensional interactive feature selection, head and neck cancer, or temporal symptom outcomes. Finally, for visual steering and interactive machine learning, prior work includes interactive clinical regression models and more general approaches for explainable machine learning and interactive rule mining, but aren't applied to radiation treatment plans on head and neck cancer patients. Our data comes from a dataset of 359 head and neck cancer patients that receive radiation therapy. We have radiation treatment plans from the time of diagnosis. In these plans, they segment each organ and calculate a 2-dimensional distribution of the dose received, called the dose volume histogram. For outcomes, we have self-reported ratings for 24 symptoms that the patient filled out during their treatment each week, as well as at a 6-month follow-up appointment. We also include several important clinical factors such as the tumor staging system and level of functionality that the patient had at their baseline, which we use as confounding variables. Our system was designed using activity-centered design to be used for asymmetric collaborative analysis, where the interface would be used directly by model builders with expertise in the underlying algorithms, with clinicians providing input and feedback. We view our modeling problem as a type of explainable AI problem that can be addressed through a combination of careful modeling and visual steering. Based on our ongoing collaboration, we identified 3 important criteria for the model itself. First, actionability. Our model needs to fit into the existing workflows of our clinicians. To this extent, we mimic the stratification system that they use to guide treatment planning, and dose guidelines that are used to provide soft constraints to treatment planning software. Second, plausibility. The internal logic of the model for each outcome needs to align with the clinician's spatial understanding of what drives each outcome. For example, a model predicting loss of taste should consider the tongue rather than the brainstem. Finally, transparency. When dealing with models in a decision-making setting, it's important that users are able to understand the model's reasoning for their decision, as well as the model's general strengths and weaknesses, in order to prevent both under- and over-trusting model predictions. For the development of our system, we distilled our previous workflow into 3 main activities. First, we do model selection, where we select the initial cluster parameters to create our spatial clusters, such as the organs and dose features. Then, we investigate the general patterns in the clusters, such as intra-cluster dose and outcome distributions, and find ways to explain the clusters for clinicians. Finally, we validate the clusters by analyzing their performance and using model explanations to see if the internal logic is consistent with clinical knowledge. This insight is then used to identify potential changes to the cluster parameters in an iterative process. This is an overview of our visual system. We have 6 main components. First, a control panel to specify the parameters and outcomes of interest. To provide information sent on possible improvements to the model, an additive effects view shows the estimated impact of adding or removing features from the cluster on the specified outcome, which allows us to quickly identify improvements to the cluster parameters. A cluster dose view shows the spatial within-organ dose distribution for each cluster. To validate the clusters, an outcome view shows the different symptom ratings over time for each cluster. The outcome view can also show the odds ratios of each cluster experiencing an outcome and whether the cluster is significantly correlated with the outcome. A configurable scatterplot view shows a 2-dimensional projection of all of the patients. The scatterplot can also be used to investigate a projection of the dose distribution, symptoms, or clinical variables. Finally, to view cluster explanations, a rule view generates a set of dose thresholds that best separates a cluster of interest. By showing these rules, we can translate our clusters into simple treatment guidelines to match how clinicians typically assess patient risk. When dealing with organ data, understanding the spatial relationship between features is essential for identifying why patterns arise in the data. To help convey the spatial information in a way that is intuitive to both data scientists and clinical collaborators, we crafted a visual scaffolding-based 2-dimensional representation of the organs of interest in the head and neck, shown on the left. On the right is an example of a simplified version of the mapping being used to show the intra-organ dose distribution for each cluster. To further ground this in domain knowledge for oncologists, we also show a dose volume histogram in the tooltip for each organ, which ties the heat map to an existing method of visualizing sets of dose distributions for each organ. To help explain our clusters, our interface uses the novel way of translating each cluster into a set of dose thresholds. which oncologists typically use as soft constraints in their treatment planning to minimize side effects. As an example, we can look at the dose volume histograms for all patients in a specific organ in the cohort, where each line represents a patient. To identify the clusters, we find an X and Y value that best separates the target cluster from the remaining clusters. In this example, we are predicting that patients that receive at least 20 dose units to 50% of their tongue are more likely to be in the high-risk cluster. We then turn this into a simplified representation of the rule by visualizing only the dose distribution above the dose value of interest. Patients above the thresholds are classified as a high-risk cluster in our mimic model. With a rule mining algorithm, we take these rules with the highest mutual information with the target cluster across all organs. For each of the best rule, we can repeat the dose thresholding process on the remaining patients that satisfy the first rule, in order to get a combined set of rules that better sorts out the cluster. This process is repeated until no further improvements are found, or a maximum number of rules are reached. By combining rules from multiple organs, we produce a set of simple rules for explaining our clusters that can also serve as an actionable and accessible model for other oncologists that don't have access to the original clusters. The main value of DASS comes from its unique functionality and ability to support clinical model development. We illustrate in the paper with 2 case studies where we develop models for toxicities such as dry mouth and swallow dysfunction. Additionally, we report qualitative feedback and user ratings from a set of data scientists. In the supplementary material, we also provide a more quantitative analysis using the system to improve models built using previous workflows. Our first case study looks at improving dry mouth prediction, which is the most common side effect in treatment. We started from a model that is based on existing dose recommendations using doses to the parotid salivary glands, using a set of dose features found from a prior grid search. Through a series of iterative improvements, we found that the model is significantly improved through the addition of the submandibular salivary glands and soft palate at the top of the mouth, which houses several smaller glands important for salivary function, but don't have established dose guidelines. Additionally, through our rule explanations, we found a set of minimal dose thresholds to the submandibular salivary glands that serve as a strong predictor of long-term dry mouth, to point to a potential new guidelines for treatment planning to reduce side effects. Through the development of our system, we identified 3 general design lessons related to dealing with clinical explainable AI development. 1. Explanation scaffolding. In our previous works, we've talked about visual scaffolding, where we build up more familiar visualizations when working with domain experts. We extend this idea to model explanations, where we focus on explaining our clusters using more familiar models such as dose thresholds and dose histograms. 2. Keep model goals flexible. While working with clinicians, we found that it was difficult to identify concrete heuristics to optimize for that best met their goals. Instead, we focused on allowing user input to balance objective measures like performance across different metrics, along with subjective measures like the plausibility of the model and usefulness of the specific cluster distribution. 3. Encourage skepticism. When dealing with systems that might be used for human users, it's important that users don't overly trust the system recommendations when they might be wrong. As a result, we found that we created better models when we intentionally added elements to the design that cued users to areas where the model might be less accurate, such as outlier cases in the scatterplot or incorrect predictions. In terms of generalizability, our solution relies on visualizations that require knowledge of the underlying models and domain knowledge needed to evaluate the plausibility of the models. These designs are head and neck specific, but could be expanded to other spatial problems where the model outputs can be translated into discrete groups, such as clustering or decision trees. In terms of scalability, our system works on a relatively small cohort of 350 patients, but could scale up. We require 5 to 15 seconds to update new results for each cluster in our dataset, depending on the input parameters. Additionally, the scatterplot and rule view show individual patients, so they may have difficulty scaling to large cohorts. In conclusion, we have presented a machine learning and visual steering system for the symptom modeling of spatial oncology data. Our design relies on 3 main principles. 1. Information sent to guide model development. 2. Visual scaffolding to help bridge information gaps between domain expert knowledge and our novel encodings. 3. Explanation scaffolding to tie our more complex models to those that our collaborators have more experience with. In addition to our interface, our paper presents a task analysis of explainable model building alongside clinical experts and lessons learned from our years-long collaboration. We hope that these findings will help future designers create better and more trustworthy models in high-stakes settings. I would like to thank my lab mates at the Electronic Visualization Lab at the University of Illinois Chicago, as well as our collaborators at the MD Anderson Cancer Center and the University of Iowa. This work was supported by the National Institutes of Health and the National Science Foundation.